So the tasks in the assignment that you're going to be given include three methods: by the product rule, the quotient rule, and the chain rule, which you're going to looking at over the next couple of weeks. They take a little bit of getting your head around, and so that might take a little bit longer to do than previous assignments. You might need to use the video clips that are on there, refer back to this lecture to get your head around the ideas behind them. But before we look at those, let's just review what we know about differential calculus already because of what we did last year. First off, there are two different ways we can represent the differential. One is dv by dt is how we'd say this. So why is it dv by dt? V because that's the what's called dependent variable, and t because that's the independent variable. So the two letters effectively in the function that you've got, and at this level you'll only ever have the two letters. One will be the independent variable, generally the one on the right, so that's the one that goes on the bottom, and the dependent variable is the one that goes on the top. So to represent the differential of this, I would say dv by dt. If the variables were y and x, then I'd say dy by dx, or whatever it is. Okay, so that's one notation we use for the differential. The second notation is this way that we write a function here, which is quite common actually, and you've probably seen functions like this. This is, say, the v function, so it might be v for voltage, and it's telling us how the voltage is changing. And what's the thing it's changing with respect to? Time. So it's some sort of time-dependent function. So we've got our two variables, v and t, here, effectively. So we don't need to start writing things like dv by dt or anything like that. And we use a prime here, a dash or a prime it's called, to represent this is now the differential. And a bit later on, and further on in your mechanics next year, if you carry on with this course, you'll be finding first, second, third differentials and so on. So this then becomes quite a nice way to write it because it's much easier to write than the notation on the left. Two ways to write the differential of a function. We did some work on differentiation last year. And if you remember, the differential tells us something about the function. I've plotted the function v equals 5e to the 3t, the one we're looking at here, there. It's an exponential function, and it looks like this curve. This is a classic exponential curve, exponential rise curve. And lots of functions in engineering obey that law, change exponentially. Anything where the rate of change of the function depends on how much you've got is exponential. And if you think about it, that applies to many situations. The rate of discharge of a capacitor depends on how much charge there is on the capacitor. The rate of decay of a radioactive isotope depends on how much there is. The rate of growth of a population depends on the size of the population. And if you think about it, that sort of makes sense. And if you look at that function, it generally looks like this. Power function, where the base of the power is this natural number e, exponential functions. So it's not uncommon to want to differentiate functions like this. Can anyone remember what the differential of a function tells us about that function?
Gradient.
The gradient, exactly right, the gradient, the rate of change. If I want to know what the rate of change of that function is there at that point, I'd find the gradient, the rate of change of that function. The rate of change of voltage with time. How quickly is that voltage changing? If I wanted to find the rate of change of this function at this point, after 1 second, say there, I'd find the gradient at this point. Well, I could draw a little triangle and work it out, and we sort of did this last year, I think, but much more quick, differentiate the function, and that tells us. And there are some little rules to tell us the differential. These differentials are written down on the table. We don't need to remember them. And last year, I think you got this table of differentials. On the left-hand side is the function. On the right-hand side is the differential. I will print out another copy so you've got it to refer to, and I'll also put it on the website so it's there if you lose it. What it's saying is if I've got something like a constant, and if we think about some examples, say the differential of a number 4, this is to remind you from last year, and if I were to plot the function y equals 4, then it would look like this, a straight line at y equals 4. And so the gradient of that line is 0 by definition. It's a horizontal line. So the gradient of any number, it doesn't matter what that number is, let's take for example 4, is always 0. And then another one would be, for example, something like ax. So it could be something like 4x. And again, if I were to plot the graph of 4x, it would look a bit like this. A straight line. And if you remember the equation of the line, y equals mx plus c, the gradient is that number in front of the x. So the gradient of a function like that is just the number in front of the x. So if I've got 4 or 4x, it's easy to say what the differential is. So in the first one, it's 0. In the second one, the x, or whatever the variable is, disappears and you're just left with a number. And then we spent some time last year playing around with this thing, which is the general one that's used most often. To differentiate a function like this, say 4x squared, what this rule tells us to do is to bring down the power, n, bring down the power, and multiply it by the number in front. That's what that's saying, a times n. So in this case, it would be 4 times 2 is 8. And then we put in our variable, which is x. And then it's just telling us whatever the power is, take one off it. So 2 take away 1 is 1. 8x to the 1 would be the answer. But of course, we don't generally write the power 1, so just 8x. And we spent a bit of time playing around with that. If you had roots, square roots, indices, all sorts of things, and it got a little bit complicated. Luckily for us, because we're focusing on these rules, power, the product rule, the quotient rule, and the chain rule, I'm not going to get into all that again. We're just going to use that basically with straightforward functions. This exponential function we've just been looking at, what happens with that? If there is a number inside with the x in the power, look, that number just comes down and goes in front. Straightforward. Once you've done a few, it's not complicated. So for example, if I had something like 3e to the 4x, for example, and I want to differentiate it, the 4 comes down. This rule doesn't tell us, though, what to do with the 3. So basically, in that situation, what this rule is saying we do is we bring down the 4 and times that by whatever number is already there. So 4 times 3 is 12. E, and then if you look at this particular case, the power doesn't change. So if it was 4x, ax, in other words, it stays as ax, and a special function. And then there's some others. Log function is 1 over x. The sine becomes cosine. You might be remembering some of these now. And whatever number is inside comes out and goes in front. So we've got a set of rules that allow us to differentiate very quickly some of the common functions. And these are the common functions. We talked about these, look. The cot function and others further down, these new trigonometric functions. I've given you some that you'll need for this assignment. So that's the way we differentiate common functions, using a table like this. So if I want to differentiate a function like y equals 16x squared, what will be the differential using that table? So this first one, well, the rule I'm going to apply is this third one down, the general one that we use. What does it say? Bring the power down, times it by the number in front. Sorry, this one, bring the power down, times it by the number in front, take one off the power. So applying it to this, I would bring the 2 down to make 32, take one off the power, 32x. What notation am I going to use? It's the differential of y with respect to x. So dy by dx equals 32x. And remember, that tells us the gradient of that function at a point. So if x equals 0.1, then we could say what the gradient was at that point. dy by dx would be 32 times 0.1, which is 3.2. The gradient of that function at the point 0.1, when x equals 0.1, is 3.2. It's exactly the sort of thing you'd be doing in the assignment, so let's just review that and check you've got it. So if I want to know what is the gradient of a function at, say, x equals 0.1, I differentiate it to get 32x, and then I let x equal 0.1, and that's the gradient. Straightforward. But the first thing I have to do is differentiate it. The second one, let's say I want to know when t equals 0.2, what's the gradient of this function when t equals 0.2? So first step, differentiate it. Same. 3 lots of 18, 54. Take 1 off the power. 3 take away 1 is 2. So it's 54t squared, which I hope you got. But what notation will we use for this? dy by d. Right. Okay. And now I let t equal to 0.2. So dy by dt equals 54 times 0.2 squared. And then I get my calculator out and work out what that is. And it tells me what the gradient of that function is at that point. A very powerful thing. If you're thinking about moving objects and you want to know the rate at which they're changing, what speed are they going at that point, for example, or what's the change in voltage. And finally, y equals 3 theta squared, theta to the minus 2 rather. That's actually how I would write, if you remember, y equals 3 over theta squared. Do you remember from last year, if I was asked to differentiate a function like y equals 3 over theta squared, I'd rewrite it like that, 3 theta to the minus 2. If I want to differentiate that function, same rule. Just because it's negative doesn't make any difference. dy by d theta this time would equal minus 2 times 3 is minus 6. Theta minus 2 take away 1 is minus 3. So that rule, you just apply the rule. Finally, the bottom one here, different rule this time. If we look back at the table, sine, that's this one here. So what happens? The number inside comes out and goes in front, and the sign changes to a cosine. And the rest stays the same. AX stays as AX. So applying that to this, whoops, oh yeah, we would have 12 times 0.3, which is 3.6, cosine 0.3x. 12 times 0.3, 3.6. Cos, sine changes to a cos, so you just follow the rule. And this time the notation would be b prime. I just made a note of some exercises you could have a go to remind yourself of them, but that's not really the crucial thing. I want to get onto the rules. Just remind yourself of those basic differentials and the table so that when you come to applying the rule, you're not struggling on this bit. So but what I want to do now is to move on to the product rule. So I said at the beginning there were going to be 3 rules we looked at. This is the first one, the product rule. What is it and when do we use it? Because you're going to get 3 tasks in the assignment, and the first thing is going to be deciding, well, which rule am I using? I'm going to try and differentiate something like this. Y equals 5x squared sine 2x. Let's look at this for a minute. It's not impossible that we would be interested in functions like this. If you remember the wave function we were looking at before we looked at this, a was the amplitude, omega angular velocity. We've got a wave function with an amplitude of 5x squared and an angular velocity of 2. this is telling me that the amplitude is not constant. It depends on x. As x increases, the amplitude increases. And you can see that happening in this wave look. As the time, or x, increases, the amplitude of the wave is increasing. So that's why this wave looks like that, because the amplitude is not fixed. When we look at it, the first thing that to strike us, to help us to decide whether we need to use this rule or not, is if x appears twice. I've got two separate functions involving x. A 5x squared function and a sine 2x function multiplied together. And if we look at our table of differentials, nowhere on that table of differentials does it talk about that. And so what I have to do is find a rule to allow us to use this table effectively. And that's the product rule. So if I've got a situation where I have two functions multiplied together, that's when I use the product rule. If I can identify two separate functions and multiply them together, I use the product rule. The problem here is that I've got two functions involving x. In cases like this, we use the product rule when the functions are multiplied together, I should say. So let's look at this function. So what about this function? Do I need the product rule in that function? Yes, why? Does it? I can only see one x. Yeah. Look at it. This is where the notation comes in really handy. This is telling me, Aidan, what the independent variable is. What is the thing that's changing in this function, x? I've got two things I don't know in here, an x and a t. So if x is the only variable, that means this must be a constant. I just don't know what it is. So there's only one variable in there. I can differentiate this without using the product rule. I just treat that as 5t times the number in front. So if I wanted to differentiate this, f prime x would be, if you look at the table, the 4 in the exponential function comes down and times by the number in front. So 4 times 5t is 20t, e to the 4x. I can do that because there's only one variable, x. X only appears once. So what about this one? Do I need the product rule for that one? How many times does t appear? No? Once. This time, the variable is t. Only appears once. This is a constant. So effectively, what I've got is a constant e to the 4x times 5. So that's like 5e to the 4x times t. So it's a constant times t. So I'd apply the rule for the constant one times t, 4x or ax, and the x would disappear, or in this case the t would disappear, and so the differential would be 5e to the 4x. Don't need the product rule because x only, in this case t only appears once. What about that one? It's there twice, isn't it? I might be tempted to use the product rule because x appears twice, but what can I do? Can I simplify that? Yeah, 5 times 3 is 15, x cubed. So in other words, if the variable appears twice, then try and simplify it. And if you can, then you don't need to use the product rule again. So that's straightforward. I could differentiate that. Let's look at the product rule now in more detail. So this product rule, let's look at it for a minute. It looks horrendous. And we'll talk about it in a minute. It's not as bad as it looks. In words, it's effectively saying, I'm going to take my function. If we look at the one we started off with, this 5x squared sine 2x function, x appears twice. And I can't simplify it. I can't combine those x's together because that's sine 2x. So I've definitely now got a situation where I've got x appearing twice. And they're multiplied together. The 5x squared is multiplied by the sine 2x. So I'm going to use the product rule. And what I do is I let one function be u. So the 5x squared I'm going to call u. And the sine 2x I'm going to call v. It actually doesn't matter which way around to do it. But I usually do it in order, u and v. And then this product rule tells me I take the first function, u, which is 5x squared, and multiply that by the differential of v, which is this. And then I add v, which is the second function, and multiply that by the differential of the first function, the differential of this, in other words. So it's just a little rule that we use. You take the first function, multiply it by the differential of the second, and add the second function multiplied by the differential of the first. And I've written that out in words here. So in words, that's this product rule stated, but that's how you would write it using mathematical notation. So let's apply it to this function. This is a really good way of setting out the use of the product rule, and I'd quite like you to use this when you do the assignment. If you choose to do it a different way, that's fair enough, but I need to make sure that it makes sense. As we talked about before, you know, if I can't understand what you're trying to do in these assignments, then I'm going to have to ask you to have another look at it. So make it clear for me what's going on. So this is how you would do a problem like this. First of all, show which bit of the function you're calling u and which bit you're calling v. And then split the page into two parts and write down what u is. U is 5x squared, and then differentiate it. Write down what v is and differentiate that. So that's the first steps. Write down what u and v are and differentiate them. So what is the differential of 5x squared? 10x. So 10x goes in there. What is the differential of sine 2x? 2 cos 2x. Good. Okay? So we take our two parts of the function, the u and v, and differentiate them separately. And that's as good a way as any I can think of to set that out. And then I'd like you to state the rule you're going to apply, the product rule. So write down the product rule, please, if you're doing this in an assignment, and which tells you what you're going to do. You're going to write down what u is, and what is u? It's 5x squared, and multiply that by dv by dx, which is 2 cos 2x, and so on. So dy by dx equals u, 5x squared, times dv by dx, which is 2 cos 2x, plus v, which is sine 2x, times du by dx, which is 10x. And it can't do any harm to write down what these are above. Certainly in these notes, so you can actually see when you look back what you've done here. Now, that is the differential. That's the differential function. And we're going to use that to find out what the differential is when x equals 6 here. So, and this is what I want you to do in the assignment as well, because this user for algebra comes into this too. I don't want you to leave it like this. You can actually simplify it. If we look at this, these are all multiplied together. 5 times x squared times 2 times cos 2x. Note, cos 2x is all one thing, so I can't separate out the cos and the 2x. And you know that, don't you? Okay? But I can multiply the 5 and the 2 together to get 10. So I can simplify that and call it 10x squared cos 2x plus, and I look at this and try and simplify that a bit further. I can't simplify it in particular. I can't combine that 2x with that because this is inside the sine function. But what we tend to do always, and if you remember back to the beginning of today, and I mentioned the wave function, that's the amplitude. and that's the angular velocity. So we always put the amplitude at the front. So I'd put the 10x at the front, and then I'd write sine 2x. So I'd want you to simplify it like that. Always put the trigonometric bit as a function at the end and tidy up as much as you can. And finally, I want you to try and factorize it. Look at these two terms. What's common to both of those two terms? X and 10. I can take 10x outside a bracket and then ask myself the question, what have I got to times 10x by to get 10x squared cos 2x? X cos 2x. What have I got to times 10x by to get 10x sine 2x? Sine 2x. I'd like you to try and simplify it down as much as possible, because then when you put the number in, i.e. when we're going to let x equal 6, we're far more likely to get an accurate answer because we're not doing too many steps on the calculator. I can do this in one hit on the calculator. Obvious that they're degrees, the chances are that these are measured in radians. So if you're putting in values into a function like this, when you're putting in numbers into a function like this, it's almost invariably the case that you're going to be measuring the angle in radians. So check your calculators in radians. So when x equals 6, dy by dx equals 10 times 6, which is 60. Well, I can do that bit. 6 cos 2x. 2 times 6 is 12, plus sine 12. And that is what I'll type into the calculator. Try not to do too many steps. Do the simple things if you can before you put it into the calculator. Now I'd get my calculator out, I'll check them in radians and then work out the answer. So 271. The gradient of this function is 271 when x equals 6. Let's look back at the function when we drew it in the first place. Remember, we were talking about this function and we wanted to find the rate of change of this function when x equals 6. Well, here is x equal to 6. What we've found is the rate of change of that function at that point, the gradient of the function at that point. And if this was voltage and time, it would be the rate of change of voltage. Or if it was some sort of sliding machine part, it would be the speed at that point, the rate of change of displacement with time. Your assignment is going to be asking you to identify which rule to use, differentiate, and then find the value for the function at a particular point, or the differential of the function at a particular point. So let's have a look at an example, and I'll let you have a go at it. Okay, here's a function. Write it down. S equals e to the 4t sine 5t. What I want us to do is to find out, or to differentiate that, please. So if I'll just pause this video and let you have a go at it. So identify which bit you're going to call u, which bit you're going to call v, differentiate each bit separately, and then apply the rule. Follow the steps that we did on the previous example. So let's have a look at this example then. So I'm going to let u equal this bit and v equal this bit by two separate functions. So I'm going to write down u equals e to the 4t, and I'm going to write down that v equals sine 5t. This is the way we do it. Separate out your two functions. Then I'm going to differentiate them both. So I want to know what is the differential of u with respect to t, and what is the differential of v with respect to t. That's when I get my table. And in the exponential function, if you look at that, you'll see that the a just comes down and the rest stays the same. So that will be 4 e to the 4t. This is similar to the one we've just done. So the 5 comes out and goes in front. The sign changes to a cosine and the rest stays the same. So it's a one-line answer. This is not complicated. Now I write down the rule I'm going to apply, which is the product rule. S by dt, well, just write down dy by dx, don't bother with it, just write down the rule. U dv by dx plus v du by dx. That's the product rule. The first bit times the differential of the second plus the second bit times the differential of the first. So I've taken my two parts differentiated and now I've written down the rule, and now I'm going to apply it. So the s by dt, which is what I want, equals u, which is e to the 4t, that's that bit, times dv by dt, which is 5 cos 5t, plus v, which is sine 5t, times du by dt, which is 4e to the 4t. What I want to do now is just try and tidy up. So I'm going to put numbers in front. So in this one, I'll put the 5 at the beginning. There aren't any other numbers, so I can't times that by anything. So that's going to be 5e to the 4t. Cos 5t. Always putting the cosine bit at the end. And again, put the 4 at the beginning, the 4e to the 4t, and then the sine 5t at the end. So I just rearrange it like that. In cases where the exponential function's been in it, when we've differentiated the exponential function, that doesn't change. So I'm always going to be able to take that outside a bracket. So ds by dt finally equals e to the 4t outside the bracket into 5 cos 5t plus 4 sine 5t. Looking back at the original function here, 5, this one, I've plotted this on autograph. The amplitude is this bit. It's an exponential changing amplitude, which is rapidly growing exponentially. So the amplitude is going to be increasing. If I plot this in autograph, I get this sort of function. This is after 1 second here. And so you can see already the amplitude is going down to -60 and then way off up. And what I'm interested in, what's the rate of change of this thing at 0.3 seconds? So I can use autograph and zoom in on this bit, which I did, and that's down here. So I've zoomed in on it a bit, and I'm interested in about the 0.3 second bit, which is roughly here somewhere. What's the rate of change of this function at that point? I've differentiated it now, so all I've got to do is say, well, so therefore, at 0.3 seconds, ds by dt equals, I just got to put 0.3 in there, replace t with 0.3. So e, 4 times 0.3 is 1.2. 5 cos, 5 times 0.3 is 1.5, plus 4 times the sine of 1.5. Run out of room. Check them in radians on the calculator. Don't make that mistake in the assignment. And then work it out. And that will tell me what the rate of change of this function is after 0.3 seconds.